second session of today's talk, and it will be the last talk of LQCD1 by Peter. Peter.
Thank you very much. So in the very first lecture, I discussed that one of the fundamental properties of Quark-Gluon Plasma is screening of color charges. So in today's lecture, I will discuss this feature of Quark-Gluon Plasma, discussing color screening in 2+1 flavor QCD. As we will see, understanding of color screening is kind of closely related to the effective field theory at high temperature, namely the electrostatic QCD. And in the last part of my talk, I will talk about spectral function and in particular about the determination of the heavy quark diffusion. So that's a slightly different topics, but kind of interesting for heavy ion phenomenology. Okay, so as I also discussed in the previous lecture, to study color screening, we consider correlation function of Polyakov loops, which then gives the free energy of a static quark anti-quark pair. And we discuss its properties in pure gauge theory, namely that it shows the linear rise with increasing distances, which means that you have confinement below the transition temperature, below the deconfinement transition temperature, and then above the deconfinement temperature, the free energy is screened, and then we discuss the screening mass. So now the question is, how does the situation look like in 2+1 flavor QCD? And I show the most recent results in 2+1 flavor QCD that has been extrapolated to the continuum limit at different temperatures. So what is shown here, the black line is a zero temperature result, extending, so to say, to very short temperature, but that's not a direct lattice calculation, only more like a guess. But overall, you see that the zero temperature results from lattice calculation and what kind of other estimates they agree. And now you compare the free energy of a quark anti-quark pair with a zero temperature potential, shown as colored symbols and these lines. And what you see is that as you go to short distances, the free energy becomes equal to the zero temperature potential up to this temperature dependent shift, which comes from just the normalization of the Polyakov loop. At large distances, of course, the free energy becomes independent of the distance. That means that you screen the color charges, so beyond some distance, the color charges don't talk to each other, and therefore the free energy is independent of R, so it's completely screened, and you're dealing with two individual static charges in Quark-Gluon Plasma, which are screened separately. Now, what's interesting, and that's new compared to pure gauge theory, is that if you go to lower temperatures, as the lowest temperature around the transition temperature, you still see that the free energy becomes independent of the distance. So you don't see the linear rise as you see in the potential, and that's because the string could break in QCD, so you could create a static quark, light quark anti-quark pair, then recombines with a static quark anti-quark pair to form static light mesons, and once that happens, then the free energy of a static quark anti-quark pair won't depend on the distance R, so the separation between these two static quarks. The other feature of this free energy, which I will kind of explain why it happens, that already at relatively short distances, you see very large deviation from the zero temperature result. So that somehow, if you look at this figure, you see that it looks like the free energy becomes very different from the vacuum potential already at very short distances, and that's something which you need to understand. And of course, there is apparent feature that as you go to higher temperatures, the distances where you kind of screen the potential becomes temperature dependent. So as at higher temperature, you screen the forces at smaller and smaller distances. So this naive expectation that the bi-screening radius is inversely proportional to the temperature, of course, holds non-perturbatively. So as I said, the free energy. So questions?
So the t equals to 0 part, is it calculated using some models? I mean, the t equals to 0 part?
No. The t equals 0 part was calculated essentially directly on the lattice, is this black line. Now, at short distances where we don't have lattice data at 0 temperature, what we did, and I will explain a little bit later, we calculated not the free energy, but the causal singlet free energy, and that has very little temperature dependence at short distances. So from that, we inferred what could be the 0 temperature potential at the very short distances. So it's also lattice actually, but it's a finite temperature lattice of a slightly different quantity, which shows much less temperature dependence. Simply because at these short distances, we cannot do 0 temperature calculation. So the other feature is that, of the features I already described, that at large distances, it approaches a constant, so that's the F infinity. So that means that F infinity, as I showed in one of the previous lectures, is related to the renormalized Polyakov loop. So namely, F infinity divided by 2 is just, and the temperature in exponent just gives a renormalized Polyakov loop. So from here, you could see what the Polyakov loop will be. So you could convert the asymptotic value of the free energy to the value of the Polyakov loop as function of the temperature. Oops, going the wrong direction. So here I show the results of the renormalized Polyakov loop in 2+1 flavor calculation. So I show 2 data sets. The one, a continuum extrapolated results obtained with Hisk formulation, another one with a Stauff formulation. And as I said, in the continuum, they better agree, and we see a pretty good agreement between the 2 lattice calculations. What you also see is that the Polyakov loop shows a very smooth temperature dependence. So you almost can't see anything going on. So it's, as you go from low to high temperature, it's just a smoothly rising curve to the first approximation. And it's very different from the Polyakov loop in pure gauge theory, where the Polyakov loop is a real order parameter. So here I show the temperature dependence of Polyakov loop SU2 and SU3 gauge theory. You see obviously a jump as a phase transition, deconfinement phase transition temperature, SU3 gauge theory. For SU2, it essentially, you can't continue. There will be a kind of, it's a second order transition, so it goes down, but it's essentially the slope is infinite. Whereas the dependence in full QCD of the Polyakov loop is very different. So in other words, the deconfinement in terms of Polyakov loop in full QCD is completely different from the deconfinement in pure glue theory. And of course, in that sense, it's not clear if the Z3 symmetry plays a role in QCD with dynamical quarks. Now, of course, the other question is, how would you ever define the deconfinement transition temperature in QCD? Because if you look, there's a chiral transition happening around 156, there is very little change in the Polyakov loop. So as a chiral transition, the Polyakov loop shows very, very smooth behavior. So of course, you have to kind of zoom in a little bit to understand anything about the temperature dependence of Polyakov loop. So it's actually more convenient, instead of the Polyakov loop itself, look at the free energy of a static quark as function of the temperature. Now zooming in this low temperature region where you may expect the transition happening. And furthermore, because the Polyakov loop now is finite, right? And it's finite because of the string breaking. So even if you go to very low temperature, the free energy of a static quark could be finite, simply because if you create a pair of a quark anti-quark in the vacuum, recombining it with a static quark gives you an energy of a static meson, and the static, because the energy of a static meson is something finite of all the lambda QCD, then it could be large, but it's finite, so you may have a small Polyakov loop, but of course the Polyakov loop even at very low temperature won't be 0. So that tells you that at low temperature, the Polyakov loop is somehow related to the spectrum of static light hadrons. So now you could try this idea and see how it works in practice when you look at the temperature dependence of the Polyakov loop, or here more precisely, the free energy of a static quark at low temperatures. So the idea is that if you have a partition function of quark anti-quark pair at some finite temperature, divided the partition function of the same system without the static quark, and that's essentially what the Polyakov loop is. At low temperature, you could write down as a Boltzmann sum of the energies of a static light mesons, or the static light QQ bar pair, taken at infinite distance. So when you separate the QQ bar pair at low temperatures, then it just gives you the energy of a static light meson minus the mass of the static quark. So now if you would know the spectrum of static light mesons in the vacuum, you in principle have a prediction for the free energy of a static quark at low temperature. So of course, now you could utilize whatever you know about the spectrum. And in fact, the ground state and first excited states of the static light mesons have been calculated on the Lattice QCD. So we know the spectrum. Then of course there is a much higher excitation which have not been studied in Lattice QCD, but you could take static, not static, but heavy light mesons as a proxy for static approximation, and there is some experimental results on that, as well as quark model prediction. So if you put everything you know about the spectrum of static light meson, you could make the prediction for the Polyakov loop or the free energy of a static quark at low temperature. So essentially adding all these states as a Boltzmann sum. So that is shown here. So in this figure, so this figure shows the free energy of a static quark as function of the temperature. You see a small inflection point in the data. So the data usually smooth, almost follow some smooth curve, but there is some small inflection point here. And now you could compare this with what you would get if the entire free energy would come from some Boltzmann sum of static light hadrons. So if you just take the ground state static light mesons, you get the blue curve. If you include additional state, the excited mesons as well as static light baryons, everything adding together, then you get this red curve, as well as if you propagate the uncertainty of all these masses, then you get the blend. And you see that at low temperature, it seems to describe the data reasonably well, but as you approach the chiral transition temperature, approach something 150 MeV, this breaks down, and the data no longer follows the expectation you would get from this kind of hadron gas of static light mesons. So something here indicates that this quantity is sensitive to deconfinement. You cannot describe it in terms of a simple hadron picture. Now, of course, you're looking at the inflection point, and in order to see where something's happening, or what you could try to define an inflection point as indicator of the deconfinement transition, and that naturally leads you to the entropy of a static quark. So typically, if you look for inflection point, you would take the derivative of this curve with respect to the temperature, and the derivative of the free energy with respect to temperature just minus the entropy of a static quark. Yes, please. Well, there is no example. It's all hadron states, but it's kind of all the hadron states which you could think about, right? So it's a kind of the spectrum of static light hadrons that has been measured on the lattice. But then, of course, you take all the quark model states. In principle, I didn't include hybrids, but those are so heavy that they hardly would affect this curve. So everything which kind of within reasonable bounds of imagination, it's included, and that's not enough. Not that I could think of. I mean, some people have maybe brighter imagination and they could think of something, but whatever I kind of could think of has been added in this red curve, and that's not enough. Of course, whatever you add, keep in mind that of course could make this curve going down steeper, but it won't have an inflection point. So, right, the shape of the red curve and the data, of course, obviously different. And yeah, you could push it maybe a little bit here, but eventually it has to break down. So, okay, so we want to evaluate the inflection point, and as I said, we take the derivative of the free energies that gives us entropy of a static quark. So now, how does the entropy look like? And we already discussed the entropy in the previous section, but here now I show the results for full QCD. So for different cutoffs, lattice cutoff corresponding to n-tau 6, n-tau 8, 10, and 12. we essentially see that the entropy peaks around some temperature and then drops as you go to higher temperature, and I would argue that that's, of course, can be understood in terms of color screening. So this behavior at high temperature, I will discuss in the next slide, so that's understood. But the interesting thing, it has a peak at some temperature, and now you could compare this peak position with what has been termed as a chiral transition temperature on the lattice, denoted at T chiral, for each n tau, because I go n tau by n tau, so it's slightly different at each n tau, because then you have to take the continuum limit, but for the comparison, it's better to stick to a fixed n tau, because then the data is less noisy. And what you see that the peak position is roughly always coincides with the chiral transition temperature at each of these n tau. Now, what you could also see that if you take the prediction of the hadron gas, which I just described, so the gas of static light hadrons, to explain the free energy, you could also calculate the entropy in a straightforward way. That gives you this black curve. So at lowest temperature, it sort of agrees with what you get on the lattice, but as you go closer to CC, you underpredict the entropy by a lot. So it tells you that somehow the curvature, what you get from the hadron gas and what you get on the lattice is completely different. So there is much more entropy kind of coupled to this static quark than you could get from the hadron gas. But probably the most important point is that if you identify this peak in the entropy of a static quark and call it the deconfinement transition temperature, then the peak in SQ, which is kind of one possible definition of deconfinement, agrees with the chiral transition, which we determine. So that is C, which I've been discussing in the previous slides. Now, of course, it's also interesting to compare the entropy for different quark masses. So we already discussed it at infinite quark mass, which means we have zero dynamical flavor. So those are the blue points shown before. So the entropy increases as you go closer to CC and eventually diverges because the Polyakov group goes to zero in pure Goose theory, so it becomes infinite. And then, of course, you could also look at different quark masses. So as the quark mass is heavy, so you could consider a world where quark mass is so heavy that the point would be 800 MeV, so that's much closer to kind of a pure Goose theory. The full QCD result then follows pretty closely the blue points. You can go to lower quark masses, it's still close, but by the time you go to the physical quantity, you get somehow the red band, right? So what you see is that there's a deconfinement transition which manifested itself in terms of this quantity, the entropy of static charge as a divergence at the deconfinement transition temperature, somehow is still present if the quark mass is heavy, so somehow you don't have very light dynamical quarks, but it kind of slowly gets washed away as you go towards the physical quark mass, and this huge peak, which is there even at 440 MeV, becomes a very, very small bump by the time you go to the physical quark masses. And of course, then you have also differences in the high temperature region between kind of the pure Goose theory and heavy quark mass theory and full QCD. So much of the deconfinement transition temperature, as you see, or much of the deconfinement aspect of the transition gets washed away as you go from the heavy world of the heavy quark masses to the physical quark masses. But some of that feature is preserved, and it's some bump survives you could use as a definition of the deconfinement transition temperature. Now, as I said, you can go to the high temperature limit, and here you would think the perturbation theory applies. So you could calculate the Polyakov or the free energy of a static quark, and the same in a trivial way also the entropy of static quark in terms of perturbation theory. And here I show different orders of perturbation theory compared against the lattice data. So the leading order, this is this red band. And of course, this formula is simple, it's just alpha S times MD times the color factor CF. You can calculate it to next to leading order, which is shown as this dashed bands. It's kind of shifted around, and then you can go finally to next to leading order, which is this purple band. And somehow the lattice data at lower temperatures, they seem to agree with next to the leading order results reasonably well, but there is a large uncertainty band. But as you go to high temperature, actually, it seems that they in between the leading order next to leading order result, eventually they start to agree at very high temperature with the next to leading result. But it's clear that the tendency of this temperature dependence can be explained in perturbation theory, which is based on electrostatic QCD only for temperature 1500 and maybe or larger. Yes, please.
Very high temperature, shouldn't it go to leading order?
Eventually it does. So the idea is if you go to infinity, then this leading order result and the next to leading order results will get closer and closer and will start overlapping. But again, once you are here, right, I mean, to get them kind of overlap, you need to increase the temperature by several orders of magnitude, because from there on the coupling runs logarithmically and it won't happen very soon. Soren? Yeah, it's in electrostatic QCD kind of, you could always, there is kind of two expansion, right? So you always separate your perturbative series in series of alpha S, which is a normal perturbative series, and alpha S over MD. And when you talk about next to leading order, then essentially it means really you're mixing those two contributions. So here you have only static contribution at leading order. At next to leading order, you have the leading non-static corrections. So it's just a small corrections. As next to leading order, next to leading order is actually only the next to leading order instead of static modes. So you could think that if you forget, let's just forget about the non-static piece, which is this black line, black dashed lines. Essentially, that's first leading order correction, and that's the first correction appears only here. Right? So if you just consider static modes, you have only two terms in the expansion, not three. So it's kind of this labeling follows the coupling in G, but it's kind of misleading in a sense. You may think it's high order, but it's not. It's just there's a first non-trivial correction is contained here. And the real problem, I guess, you may ask why it doesn't agree better, is because the non-static contribution is known only to leading order, right? So actually, if I look only the static, I could have one more correction. In fact, I could evaluate the EQCD non-perturbative lattice, so I know it fully non-perturbatively. The problem, I cannot match it well to get compared to the lattice because I only know the first term in the non-static piece. Okay, so now let's look more into detail of how the free energy of a static quark and anti-quark depends on the distance and how it kind of shows the color screening at high temperatures. And again, here it's important to kind of make contact and decoupling calculations in order to understand what's going on. In particular, why you have such large deviations from the vacuum potentials even at very short distances. So if you think about what's the physical interpretation of a free energy of a static quark and anti-quark pair, it's essentially the work you have to do to separate a quark from anti-quark, which were at distance 1 to distance 2. So the difference in the free energy calculated at distance R2 minus the free energy calculated distance R1 is the amount of work you have to do to separate them from distance R and distance 2. You can calculate it leading order in perturbation theory. And in leading order of perturbation theory, you see that the free energy of quark and anti-quark is proportional to alpha S squared, 1 over R squared, and exponent 2 times the Debye mass, plus some finite term, which is essentially the free energy of a quark and anti-quark, which have been separated to infinity. Now, if you do the same calculation in QD, you recover the screened Coulomb potential, so you cover type potential with the screening governed by the Debye mass. So you see that the leading order QCD and the leading order QD are totally different. In one case, it's just as what you expect naively. It's a screened Coulomb potential. In other words, in the other case in QCD, it goes like 1 over R squared and twice the Debye mass. So now, to understand it, you have to realize that in QCD you have additional degree of freedom compared to QCD. You have color, and if you have a quark anti-quark, in principle, you could think of it as being either in singlet or being in an octet. And there could be possibly a cancellation between a singlet and octet contribution. So once you have an octet, QQ pairs, they don't attract each other, but they repel each other. So the amount of work you have to do in order to separate them thus is reduced compared to your naive expectation if you have only QQ bar in singlet. So intuitively, you kind of understand this reduction in the free energy because octet configuration could appear in the intermediate step. So in part of the way, when you do this quasi-static experiment of separating a quark and anti-quark, often they flip the sign of that kind of relative color sign to octet, and then the attraction is repulsive, so you don't have to do the work. They kind of pull themselves away from each other for part of the time. Now, if you want to kind of do the calculation to show it, what you have to do is to use a Firth identity. So when you have the Polyakov loop, you have this type of combination, right? You have traces of individual Polyakov loop, and then using this Firth identity, you could kind of show that the Polyakov loop correlator, which gives you the free energy, can be written in terms of the singlet contribution and the octet contribution. And the octet, because you have here the generator of SU3, and the singlet contribution is just given by the trace of two Wilson lines separated by some distance r, and I remind that the Wilson line and the lattice is just product of the link variables along the time direction. So now you could calculate this singlet and octet contribution individual in perturbation theory at leading order, and you see that they just what you expect. They're screened, so like QED form, the screen Coulomb potential with the screening governed by the Debye mass, and of course you have the color factor. In one case it's attractive, 4/3, and in the octet it's repulsive, 1/6, and of course you have the F infinity. So now if you plugged in this form, this singlet and octet expression into this formula that you derive from Firth identity, you see that you recover the leading order result for the singlet, for the free energy of a quark anti-quark. In other words, there is indeed a cancellation. So you just put the exponents in the leading order terms cancels because of this color factor and this color factor. And what you have is kind of the next term in the expanding of the exponents. So this intuition was correct, at least to leading order perturbation theory, but the problem is that in order to define the singlet free energy here, right, you trace over Wilson lines, and this object is not gauge invariant. So in order to write down this decomposition, you should have assumed some gauge. So you have to fix the gauge before you could write it. Although it's intuitive, that's of course unsatisfactory because somehow this decomposition appears to be gauge dependent, or is gauge dependent. And the question is, can you somehow understand this decomposition in more general grounds? Although you have to, at leading order, there is no gauge dependence, right? Because it depends on alpha S and Debye mass, and Debye mass is always gauge invariant, so you could calculate any gauge. MD is what is GT. So at leading order, gauge dependence doesn't appear. So in that sense, at leading order that holds, but it's somehow unsatisfying that in general, if you go beyond leading order, you don't understand what happens to gauge dependence. So the question is, can you somehow understand this decomposition of your free energy in the singlet and octet contribution on more general grounds? And the answer is yes, if you consider an effective theory approach, namely the potential NRQCD. So the idea is here that in NRQCD, you can integrate out the heavy quark out of your theory, so you have non-relativistic theory. But if you have distances between the quark and anti-quark, which is much smaller than any other scale in the problem, let's say lambda QCD or 1 over the temperature, then you could integrate out also the inverse of the distance. That gives you an energy scale, which you can integrate it out and arrive at an effective theory, which is called potential non-relativistic QCD. And in this effective theory, the degrees of freedom are soft gluons, which have energies which are much smaller than the inverse separation between the quark and anti-quark pair. And the other degrees of freedom are the meson fields or static meson field from some quark anti-quark, which could be either singlet and octet. And the octet now, of course, is fine because it still couples to very soft gluons. So if you write down expression of the Polyakov correlator in this effective theory, or equivalent with exponentiated free energy, then you see that it's, well, the only possibility you have is either it can be expressed in the correlation function of a singlet meson field, now propagated in time up to time 1 over t, so you go around the lattice, around the periodic boundary, or and the octet field, but because you go around the periodic boundary, you have the Wilson lines, which is always coupled to the octet field, and once you go around the boundary, it becomes a joint Polyakov loop. So you have the joint Polyakov loop, multiplying the octet contribution, the octet correlator, which is gauge invariant now because you went around the boundary, so it's kind of local in time in a sense. And then you could calculate this correlation function, each of them being gauge invariant, and this is kind of the PNR QCD version of the singlet and octet free energy. And you could calculate them kind of in straightforward ways, has been done in this paper. And you see that the singlet free energy just gives you the vacuum potential, the singlet vacuum potential, plus corrections, which goes proportional to alpha s, and the expansion parameter, which is multiple expansions r times t squared. And the same is for octet, except it gets shifted by this constant, which comes from the fact that you have an adjoint Polyakov loop. Now, what you could further show is that if you do a calculation in fixed gauge, you calculate in singlet and octet terms, then they're related to the singlet and octet free energies of PNR QCD, which are gauge invariant, up to corrections, which again suppressed. So in other words, this naive decomposition of your free energy in terms of singlet and octet contribution, and the gauge invariant, which come from small QCD, which is applicable at very short distances, are sort of equivalent. And therefore, now you could kind of say, well, can we test all these ideas quantitatively? Of course, if you go to distances which are much larger than the inverse temperature, or comparable at least, or say let's order the Meyer scale, of course, all this calculation doesn't apply, and there you have to use an effective theory, and that namely electrostatic QCD. But let me first go to the short distance limit and understand to what extent this idea applies, and when actually the medium effects start to be important in the interaction between static quark and anti-quark. So first of all, one could ask the question, if you calculate the singlet free energy, how is different from the vacuum potential? Because we expect these differences to be small. Right? To the first approximation, the singlet free energy should be given by the vacuum potential. And here I show the lattice data of the potential calculated at 0 temperature minus the singlet free energy as functions of distance are now in units of the temperature. The calculation have been done at several lattice spacing and extrapolated to the continuum limit, which is kind of shown as this this band. And of course, we did different continuum extrapolation shown by the points, and they all lie within this band. So with this band is a pretty good representation of what we get from the lattice. And what you see is that at short distances, the difference between singlet free energy and the potential is basically 0, or at least is very small. So up to distance 0.3, there is no difference between the 0 temperature potential and the singlet free energy. There is some difference at the shortest distance, which we understand because there are higher order corrections, which I kind of written down here. So in particular, you have some constant shift of the singlet free energy respect to the vacuum result proportional to alpha s cubed. So it's a small effect, but you now can see it on the lattice, so it's a 10 MeV shift. But apart from that, essentially it agrees with the vacuum potential. And then, of course, if you go to distances larger than 0.3 units of the temperatures, then you start to see very large deviation from the vacuum results, and that's where the color screening sets in. So up to this point, it's the quark and anti-quark interacts like in the vacuum, but as you go to larger distances, essentially you start to see that the medium effects become very important. Now you could use the PNR QCD result to understand the free energy of a quark anti-quark pair. So that was a singlet free energy. Here it was simple. It's just you have nothing or some onset of the color screening. But in the singlet in the free energy of a quark anti-quark pair is more complicated because now we have a singlet and octet contribution. So the singlet contribution to the first approximation is just like in the vacuum. So it's given by Fs, and Fs is essentially up to small corrections is just Vs. So that's you can estimate. The octet contribution, of course, you don't calculate on the lattice, but in V coupling framework you could also calculate. So in the V coupling framework, F octet is just given by the singlet, scaled by the Casimir, and the three-loop correction, which has been calculated in the vacuum in perturbation theory. That's also known from other works. So now if you plug that in and you use this decomposition formula, you could compare this PNR QCD decomposition formula with the lattice results. So the lattice results shown as the red symbols. And then you use the decomposition formula first at leading order, by just using this relation between singlet and octet, the leading order perturbative relation. You get the green curve, which sort of looks similar to the lattice data, but doesn't quite capture. Once you include the scaling, which goes beyond the naive Casimir scaling of the color factor, then you reproduce the data very well with this LQCD factorization formula up to distances like 0.3. So in order to understand both the singlet free energy and free energy of a quark anti-quark pair, the distances are like 0.3 in temperature units. You only need vacuum physics. You don't need to worry about medium effects. And once you go to larger distances, then of course you start to see significant temperature dependence, which needs to be understood. Okay, so now let's go to the larger distances and try to see to what extent we could understand now the onset of color or the color screening in terms of the singlet free energy and free energy. And here, of course, what is good to look at is essentially this, subtract this constant. So from now on, I will show all the results in these bar quantities, where you take the free energy and subtract the asymptotic constant. And of course, this quantity then should go down exponential to 0 if there is color screening. Both for the singlet free energy and the free energy has been calculated to next to leading order in perturbation theory. So now you could confront this next to leading order result with the lattice data. So here I show the results for the free energy. The lattice data shown as the symbols of the red and green symbols, and then the leading order and next to leading order prediction are shown as the dashed and the solid bands, and the uncertainty of the band essentially is the scale uncertainty you have always in the perturbative calculation. So the first thing to notice is the leading order result is quite off. Although it kind of describes the shape of the lattice data tells that, well, as you go to larger distances, that's logarithmic scale, so it's approximately linear. That's what you would expect in terms of color screening. But the absolute magnitude is off. Once you include the next leading correction, essentially with an error bar, you start to touch the lattice data. So in this intermediate distance region, you could understand the color screening of charge in terms of the free energy using the next leading results or the results quite well. If you go to larger distances, of course, you may be sensitive to magnetic screening, but in that case, anyway, the errors on the lattice data is pretty large, so you're not so sensitive to the effect. So to the first approximation, you see that the R dependence of your lattice data is described reasonably well with a next leading order decoupling calculation in electrostatic QCD. So the same thing can be said about the singlet free energy. Here is you have a simple expression. Again, there is next to leading order correction kind of encoded in this function f1, which has been calculated. And again, what you see is that the shape of the curve at intermediate distance is kind of more or less the same in EQCD calculation, in the decoupling EQCD calculation of the lattice. The absolute value is off if you use a leading order result. Once you include the next to leading order correction, you again have a very reasonably good agreement between the lattice and EQCD prediction. So at distances, let's say about RT to 0.6, you will see the onset of medium effect, and these medium effects could be understood in terms of electrostatic QCD, whereas the screening effects are encoded in the value of the Debye mass, which can be calculated perturbatively. So the screening in this distance regime is what you expect, whereas if you go to much smaller distances, smaller than 0.3 in RT, you recover the vacuum physics. Okay, so now EQCD was successful in understanding, to some extent, the bulk thermodynamic properties. So I showed the comparison of the pressure energy density with EQC prediction and perturbative predictions that worked well. We could understand the onset of color screening and the color screening in intermediate distances in terms of EQCD. So the question is, what else can we do with EQCD, which maybe goes beyond purely decoupling or pure perturbative arguments? And the interesting thing to look at is a spatial string tension. So as I said in very first lecture, or maybe the second lecture, then you could consider Wilson loops. And Wilson loops are, in some sense, order parameter of deconfinement. If you have a confinement, the Wilson loops show an area law, which means that the Wilson loops, the logos of Wilson loops proportional to the area of the loop. So that's true at zero temperature. Now, if you look at the Wilson loop, which purely spatial, so it don't go in time, so typically we think about the Wilson loops as going in time and space, but you could imagine a Wilson loop just purely spatial. What happens to those Wilson loops? And the statement is that those Wilson loops always obey the area law. So in a sense, there is no deconfinement in that sense in spatial directions. And the area law is governed by what is called the spatial string tension, which could be temperature dependent in principle. And at low temperature, so particularly in the temperature below the transition temperature, we know from the lattice that spatial Wilson loop is always more or less equal to the zero temperature Wilson loops. And above that, something happens. And here I show the lattice results on the spatial Wilson loops as functions of temperature. So T naught here is a proxy. It's not exactly equal to the transition temperature, but it's a proxy for the transition temperature. And indeed, at low temperature, it's more or less compatible with a zero temperature result. So I show now the square root of the spatial string tension in units of the Sommer scale, so which is a fixed number, so that this line is a zero temperature result, and the lattice data at low temperature is just around the zero temperature result. And then as you increase the temperatures, first is decrease, and at sufficiently high temperature, which is about 1.5 Tc, you see this linear rise in the spatial string tension. So now the question is, can you somehow understand this linear rise of the spatial string tension as you go to high temperature? And here, of course, EQCD becomes handy, because in EQCD, the spatial string tension is given by the only dimensionful quantity, relevant dimensionful quantity, and that is a gauge coupling of your three-dimensional gauge theory, G3, and for dimensionless reasons, it has to be proportional to G3 to the 4, because the string tension has the dimension 2, and G3 squared, it has the dimension 1. So you immediately see the string tension should be proportional to the temperature times the coupling, the temperature squared. So here we show the square root of the string tension. That obviously should be linear. So you indeed kind of understand this linear rise just on dimensional grounds if you assume that EQCD is the right framework. Of course, as I said, the temperature dependence kind of follows this expectation that it should be linear. Now, of course, you could go one further. There is a coefficient of proportionality, and that is non-perturbative. That you cannot calculate possibly perturbatively, but you could do lattice calculation of your EQCD in the three-dimensional gauge theory, and you could estimate this coefficient to reasonably good accuracy. So then, of course, everything is fixed. The gauge coupling of your EQCD you could calculate perturbatively has been down to 2-loop by line, actually 3-loop by line and Schroeder, so that we know very well. So the temperature dependence of this coupling is known, next to leading order result, and this coefficient of proportionality is just the string tension in units of the coupling has been calculated in lattice QCD, now in three-dimensional gauge theory. So you combine these two, and now we can confront this prediction of EQCD with the lattice results, and this is shown in this figure. So I show temperature divided by the square root of the string tension. The black line is a prediction of EQCD. And of course, because you have some residual uncertainty due to scale, you vary the scale by a factor of 2 around the 2 pi, around its optimal value, nominal value, then you get the dashed line. So that's essentially the uncertainty band of your EQCD calculation. And the different symbols are the lattice results calculated for different cutoff. You don't see much cutoff dependence, so the first approximations are close enough to the continuum. You see that all the lattice results in this band. In other words, as I said, the temperature dependence of the spatial string tension is essentially perturbative because the coefficient, the non-perturbative information is just coefficient of the proportionality, Cm, which you know, but how it depends on the temperature is all encoded in the gauge coupling, which is calculated perturbatively, and that seems to be reproduced very well by the lattice data, actually down to temperature which are surprisingly low. So in principle, if you take at face value, you would say that it even works down to the transition temperature. Any questions? Yeah.
So is there a relation between quark, anti-quark free energy and Cornell potential in medium?
Not really. I mean, at low temperatures, if you go below the deconfinement or the Carnot transition, maybe yes. But in general, the answer is no, right? Because the Cornell potential, it assumes a string term plus a Coulomb term. Yeah. And if you go to high temperature, the free energy is not Coulombic. It goes like 1 over r squared. So the Cornell potential is just a simple model, and certainly, well, it parameterizes very well the lattice data on the 0 temperature potential, but it cannot possibly account for the behavior of the free energy in the deconfined phase. Okay, so, yep. Which result? Well, I mean, yeah, actually, that's right, a good question. So Schroeder actually calculated up to 4 loop, and only for pure glue theory, but the next correction is tiny. So that's already pretty good, right? And if you could go 1 order beyond, which Schroeder did, it's basically. Yeah, because it's not surprising, right? I mean, all these parameters, G3, MD, they are kind of expansion in alpha, right? Or maybe alpha over pi, and they have a reasonably good convergence. So if you go beyond certain order, beyond the leading order, next to leading order, you are fine, right? So in a sense, it's as good as it gets, right?
Now, is it really T in the running, or is it?
Well, it's some scale. Well, it's not really T, right? It's just nominally T. It's this G3 squared will depend on some scale mu, which could be arbitrary. In principle, you choose it to be 2 pi t because that's a typical argument on the logarithm, around 2 pi t, let's say, and you vary it by factor 2. Of course, there is a scale dependence here, but then the scale dependence gets cancelled by higher order terms. So eventually, the scale dependence of this prediction is shown as this dashed line. It's not too big.
That's what the dashed line is.
Right. So that's a scale dependence. So in a sense, it tells you how good is a perturbative prediction. And at the moment, the perturbative prediction, I would say, maybe as good as uncertainty in the lattice data. We could improve on the lattice a little bit. Sure.
Yeah, but my question is, when you go to order G to the 4th, are you doing 2 loop running as well?
Yes, yeah,
okay.
2 loop running.
So it is really 2 loop.
Yeah, so it's loop. Yeah, and somehow this linear rise of the string tension, because it's purely magnetic, right? So it's purely spatial. You would say, well, it's somehow it's related to the fact that the magnetic fields are screened, but then totally non-perturbative. But the fact that the magnetic physics depends on the scale is somehow what you would call magnetic screening. Now, of course, you could apply EQCD to calculate the pressure of the systems. That has been done by Sayantan et al. A while ago. And the EQCD results now, it's full EQCD, so the EQCD has been calculated non-perturbatively. The only thing which is missing is a perturbative g to the 6, which in principle can be calculated, but it's very hard. It takes 3 years probably to calculate for Schroeder. It has a kind of pretty small uncertainty, and I'm not sure if it's fully accounted for, but if you go to the temperature, the highest temperature where you have lattice data available, it seems to agree with the lattice reasonably well, although it doesn't work at temperature below like 40 C, which may be not unexpected. The other things you could do is to calculate electron screening mass in full 4D lattice calculation, calculate on the lattice in 3D calculation, and compare the two. So here I show such a comparison. So I don't show the 4-dimensional lattice result, I just show the parameterization as this kind of dashed line, and then the temperature dependence of the electric screening mass coming from the 3-dimensional calculation shown as this open symbols and closed symbols depending on which lattice spacing you use, and essentially they agree very well. So this running of the electric mass in EQCD has been also tested quite well. Okay, so I get that's in particular that's SU2 gauge theory. That's SU3 gauge theory. Yeah, so you may say that, of course, it's not a completely kosher comparison because they somehow fitted the g to the 6. So where this curve lies depends what you assume for uncalculated g to the 6 to some extent. So if you want to, so you really, if you leave the g to the 6 free and allow it to vary within a certain range, then the certainty band of EQCD will be larger. So it's somehow maybe too optimistic, that's what I meant. Okay, so in the remaining time, I will try to talk about transport, heavy quark transport, and spectral function in general. What we can calculate in lattice QCD is Euclidean correlation function of some current. So the most interesting current for physics applications is the vector current. So we could calculate the correlation function of the vector current as the lattice Euclidean time. Of course, what we're interested mostly is this correlation function in real time, where you could define the Weidmann correlator, d larger and d smaller, of the same current now in Minkowski time. And from this Weidmann correlator or the retarded correlator, you could define the spectral function either as the imaginary part of the retarded correlator or the difference of the Weidmann correlator in the Fourier transform of the Weidmann correlator. Now, the spectral function often has intuitive interpretation. For example, if you go to vacuum physics, and the spectral function vector current is nothing but the famous R ratio of the total cross-section of E plus E minus going to hadrons divided by the total cross-section of E plus E minus going to muons divided by omega squared. So now the idea behind kind of trying to study the spectral properties or the transport coefficients of the lattice is the fact that the Euclidean correlation function is just an analytic continuation of the Weidmann correlator at imaginary argument. So if you replace t by I tau in the Weidmann correlator d plus, you get the Euclidean correlation function that you can calculate on the lattice. And from this relation, you could derive a spectral representation of your Minkowski or your Euclidean time correlation function in terms of spectral function and some integration kernel. And that essentially is the essence of how you could get access to physical quantities from Euclidean lattice calculation. In zero temperature, we always use this relation implicitly. Of course, there it's simple because we always assume that the spectral function is given by some discrete set of states, which are kind of different hadronic states that present in QCD. So you write the spectral function as some of the kind of eigenstates of Hamiltonian, so some bound states. And then you could write your Euclidean correlation function sum of exponential. You go to large time and you can project 1 or 2 or 3 exponential depending how hard you work. So there, of course, the inversion problem is simple. You just need to fit the correlation function with some ansatz, because you know the formal spectral function should be like this. Now at finite temperature, it's not clear what the formal spectral function would be. You would think the spectral function could have some features, some peaks, but those will kind of could be some washed out peaks, and of course at different frequency regions you have different sorts of peaks. So in general, this function sigma of omega could be quite complicated. So it's not possible to kind of simply extract the spectral function, and people will try to do in the finite temperatures, try to somehow invert this relation using some Bayesian approach, like the maximum entropy method, and infer what the spectral functions should be for a given set of data, lattice data on the Euclidean time correlation function. Of course, that's a very difficult task, because the maximum time extent on the lattice is limited by the inverse temperature. And therefore, as you go to higher temperature, where you want to see some interesting physics, some interesting medium dependence of correlation function, you have shorter and shorter time to resolve your interesting physics. So that's kind of where all the difficulty lies upon. So now if you look at the vector current spectral function, it has several interesting properties at finite temperature. So here I show kind of the sketch of the spectral function as function of the omega. And in principle, if you go to very high, so let's suppose we're working at very high temperature where you see there is no hadronic states remaining, then if you have a quark mass m, then you would say that at some frequency, which is the threshold of the quark pair production, to m, you have some continuum of quark states, which goes to infinity. So you just produce a pair of quark, and that's essentially the spectral density over there. If you have kind of you lower the temperature, eventually some bound states may pop up around 2m, and followed by the continuum. But what's also interesting is the part of the spectral function which goes to very low frequency. At a very low frequency, you would expect to see a transport peak. So you have charges in the system, in your plasma, you have currents, and kind of that manifests itself in the low frequency part of the spectral function. Namely, what you expect, you should have a transport peak at very low frequency. And the integral under this transport peak is nothing else but the charge fluctuations. So, or in other words, the quark number susceptibility, which we discussed in one of the previous lecture. So the kind of most general ansatz for the low energy part of the spectral function, which we often call the transport peak, that you could write is something that's proportional to the quark number susceptibility. And the transport coefficient itself, which you can think of some charge diffusion coefficient. If you have a heavy quark mass, then the width of the transport peak given this parameter eta, which is the inverse of the diffusion constant T over n. And if the heavy quark mass limit, you could identify this eta as the drag coefficient of your heavy quark in the medium, where the D would be the spatial diffusion coefficient. The momentum diffusion coefficient, again, can be calculated using the Einstein relation, and again is related to spatial diffusion coefficient by this relation. Now, of course, if you ask the question where the information about the transport is encoded, of course, the area under this transport peak tells you overall what are the charge degrees of freedom, how much they fluctuate. So that's kind of a Boltzmann observable, which you just can calculate by calculating the derivative of the pressure with respect to chemical potential. So that part we know, but the real-time information is really encoded in the width of the transport peak, because the width of the transport peak being proportional to eta is somehow related to the spatial diffusion coefficient or the relaxation time in your system. In perturbation theory, you could say that this coefficient is you could show actually that it's proportional to 1 over g to the 4 power t. That means in the big coupling, the relaxation time is very long, and therefore this transport peak is very narrow. As you go to a stronger coupling, of course, this peak gets washed out and maybe wide enough that you could even calculate on the lattice. But there is another problem. If you work at the heavy quark mass limit, as m is large, then no matter how g is large, eventually t over m will be small, and therefore you will always dealing with a very narrow transport peak, which of course will be very difficult to reconstruct from Euclidean correlation function, because essentially you can't distinguish from the delta function. For all practical purposes, if the quark mass is heavy, this transport peak is just will appear as a delta function. You won't see its internal structure, so you wouldn't be able to extract, so to say, the relaxation time or the transport peak, or the width of this transport peak, which would give you somehow the heavy quark diffusion. So there is a way out, because you could use this problem that working with a heavy quark mass to your advantage, because if you have a heavy quark mass, it means you have a heavy degrees of freedom, which you could integrate out and maybe simplify your problem. So if you integrate out the heavy quark mass, you assume the quark mass is much larger than temperature, you integrate it out, then you could reduce this current correlator to the correlation function of the field. So the idea is that you could define in the heavy quark mass limit the kappa as a correlation function of a current or derivative of the current correlator, and in the heavy quark mass limit, it just reduces, derivative of the current just reduces to the electric field. So eventually, instead of calculating the current correlator itself in the very heavy quark mass limit equivalent, you can express the correlation function in terms of the correlation function from electric field. So that, of course, this expression then, so you first, of course, take the heavy quark mass limit, and then you integrate out the heavy quark fields phi and theta from your correlation function, and then you add up this electric correlation function, which now connected with the Wilson line to make it gauge invariant. So now this correlation function, or the corresponding spectral function, has a much different properties. So in particular, it doesn't have a transport peak. So if it's in leading order perturbation theory, as was shown in this paper by Caron, Huo, and more, it doesn't show a transport peak. Instead, it kind of smoothly goes to zero at zero limit. And of course, if you go to the next leading contribution, it goes to some finite limit. So there is no transport peak in this. And in this correlation function, but instead the intercept of this curve, which kind of smoothly related to the high frequency part, gives you the transport coefficient. So in that case, all you have to calculate is a correlation function, reconstruct the corresponding spectral function, and calculate the heavy quark diffusion constant as the omega equals zero limit of the corresponding spectral function divided by omega. So of course there is a problem. Life is not as simple. So of course it's easy to realize this correlation function as a lattice. So
what is this full result and the red curve below?
So then there is different. So you have a contribution from Landau cuts and the pole, and then of course when you add them together, then you get, well, first of all, you get this, that's a full result, so that includes everything. That's only from the Landau cut of the half thermal propagator, and then you, asymptotically, it goes like omega squared from the thermal part. When you subtract it, then you get the red one. So it's just different contribution, but the bottom line is that you don't have something which peaks, but it goes smoothly from high frequency to zero. And if you calculate the next leading order, it actually goes to kappa.
The last part of the function.
Yes, of course, but then you have to go to next leading order. So that's the leading order, it just trivial. But I mean, the purpose of this just shows that there is, right, at leading order, if you calculate the leading order, the current correlator, you get the susceptibility. And here you have nothing. So that was the purpose of kind of showing it in this way. Okay, so you have now to discretize on the lattice, and of course, since you have insertion of electric fields into the Wilson lines, those are represented by some plaquettes. So the object that you have to calculate is a Wilson line, becoming a plaquette, continuing as a Wilson line till it hits another plaquette, and kind of going further down, and then everything else kind of wrapped around the boundary. So it's essentially a periodic version of electric, chromoelectric field strength correlator. And being gluonic observable, it's very noisy. So it's straightforward to discretize, put it on the lattice, but the problem is that pure gluonic quantity is very noisy on the lattice. So you have to work hard to kind of actually to be able to calculate it on the lattice. And here I show the problem. So if you calculate this object on the lattice, you look at the kind of distribution of your correlation function on configuration by configuration basis. You have huge fluctuations shown as this blue dots, right? So from one configuration to another, there is fluctuation are huge. So you have to do a huge number of configurations somehow to get rid of this fluctuation and get something which averages some small value, which is close to zero because of the lattice spacing will go to zero. So that's got to be a number which is very small, but in each configuration you get some large number either positive or negative. So you need to use novel kind of sophisticated algorithms, which so far only available in pure gauge series. So one algorithm was invented by Wisher, that's a multi-level algorithm. And then, of course, it can be combined by the link integration algorithm. And each of those tricks reduce the noise. So if you impose the multi-level algorithm, you go from the blue points to the orange ones. If you do link integration, it also reduces the noise or to a lesser extent. And if you combine the two, then you get, instead of these huge fluctuations, you get something which is this black line, so where kind of fluctuation much reduced. So with this, you could calculate this correlation function reasonable amount of time. And that has been done in series of paper by Francis, Kaczmarek, and Weiner. And the final result is shown here. So they actually calculate this correlation function. What is shown here is a correlation function of this electric field correlator calculated on the lattice. And because it's kind of a very steeply falling function, it's worth to normalize by the leading order perturbative result, which is shown here. It has been calculated by Weiner. And you see a large enhancement of the leading order perturbative result. And they also did calculation at several lattice space, eventually estimated the continuum limit, which again is well above the leading order result, but even any of these perturbative results. So now the question is, you have the data, you see this enhancement about the compared to the next leading result. Can you get the transport coefficient? Here, what they did was to find an ansatz of the spectral functions that may kind of describe the data. So what we know from the theory is that at low frequencies, the spectral function should be proportional to kappa times omega over 2 times t with some coefficient. Whereas the high frequencies, the entire spectral function is essentially given more or less by the vacuum perturbation theory. So it's proportional to omega cubed times the coupling constant. So the idea was to take these two limiting cases of the spectral functions and try to combine them in the middle some way. And of course, there is no unique way how you do it. So you just try to see all the possible ways you could kind of smoothly combine the high frequency behavior with the low frequency behavior. And of course, that allows you for a range of intercepts around omega equals 0. So they did this calculation, so I forgot to mention, they did this extensive calculation at 1 temperature, because here they had to do many lattice spacing in order to get the continuum result. And of course, now you have to fit this continuum lattice result with different forms, which are of the spectral functions shown here, which have different intercept. And here is a kind of combination of all the fit results that they considered. Of course, you have a large spread, but on the average, you could kind of map out the region, which is most likely be the value of the kappa that is compatible with lattice result. And from the estimate, it follows that the intercept lies somewhere between 1.8 and 3.4 times t cubed. So you get an estimate of kappa, which is within factor of 2, kind of constrained by the lattice QCD in pure glue theory. Now, of course, if you wouldn't consider the heavy quark, but you would consider a light quark, you could also do a similar exercise. Of course, you wouldn't integrate the fields. You instead try to resolve the transport peak, and as that has been done in this paper. And again, the first kind of interesting outcome of this calculation was that actually you do see a transport peak in the case of light current correlator. And it's why it's not kind of very narrow. You don't expect it to be narrow because the coupling constant is not large. You still do see it in a strongly coupled theory. You wouldn't see a transport peak at all because the transport peak will be so big that it will kind of smoothly merge to the kind of the rest of the high frequency part of the spectral function. And the interesting outcome of this calculation that you could estimate, well, you could see the transport peak and you could provide some rough estimate of the width, which probably accurate up to a factor of 2. So you also, the other transport coefficients that you could calculate of the lattice empirical theory is electric. In that case, it will be the electric conductivity and it's also known up to a factor of 2. So I will stop here and then take questions or then other topics.
Any questions, comments?
So is it a generic feature for any perturbative or non-perturbative QCD with quasi-particle-like picture that they will have a transport peak?
Yes. So any quasi-particle, any weakly coupled, you have a transport peak because essentially you have some free charges and they fluctuate and essentially then you have a separation between transport and the rest. In the strongly coupled theory, that's not the case. I mean, in fact, if the only strongly coupled theory we know, this calculation can be done is n equal for SUSY. N equal for SUSY could show that, for example, the correlation function of the conserved charge or the spectral function of conserved charge doesn't show a transport peak. You have a kind of non-zero intercept at omega equals 0, but it's kind of smoothly connected to the high frequency part. So there, of course, so the first question to answer, is QCD, let's say at 1.5, this is more like a weak coupling picture where you have a transport peak and the rest of the spectral function, or like in this strongly coupled super Young Mills, where it's kind of all washed in together and you have this non-zero intercept. And this lattice data indicates that it's closer to the situation where you still have some transport peak.
And in the previous slide, there were also results from the TIFR group along the same time. So how does it?
Much earlier.
Yeah.
But they didn't do the continuum result and they didn't kind of explore all the possible fits. They didn't constrain. I mean, here they use the next leading order results, whereas in TIFR they just use the leading order omega cubed as a combined with the leading order results. So they use a very simplified ansatz. Of course, you could do it, but then, of course, you never know what the systematics is.
How much the result changes?
They're pretty much compatible with an error. So this result, here they, of course, did an extensive study and they're very conservative, right? So you have a factor of 2. They say, well, we could only estimate kappa within a factor of 2. And this factor of 2 seems to cover the other lattice results very well. I mean, there is other results which, of course, that was by Ding et al., where they took the strategy from the light flavor diffusion coefficient, or so the electric conductivity calculation, the identity transport peak, and tried to apply it for charm quarks, saying that whether the charm quark is not too heavy, maybe we could resolve the transport peak. I think they can't because in their case, the transport peak in the charm sector and in the light sector is about the same. Now, it's very difficult to imagine that could be the case because even charm is not so heavy. There should be at least a factor of 2 difference between those, which they don't see. So, and that points to the fact that, of course, if you have a very narrow transport peak, you do some sort of maximum entropy analysis and Bayesian analysis, try to smear the peak, and it's very easy to overestimate the peak by factor of 2. So therefore, they essentially have a very, given the quark mass, they have a very broad transport peak, and therefore they get, which means that you have to have some very strongly coupled plasma, which would then contradict to this statement here, right? Because that says, well, you have a very well-defined transport peak, so it's at least quality is a weakly coupled plasma. If you can see a transport peak in the charm sector, that means that the diffusion constant D should be so small that it essentially compensates for your heavy quark mass, which could only happen if you take it to the extreme value quoted by this strongly coupled plasma believers to be 2 pi T, which is 1 thermal wavelength.
Any other questions? Yeah.
cannot hear you.
Why the smaller quark mass imply a broader SQ peak?
Yes, so that's exactly right. So if you go, let's go back to the figure. So you see here, well, at infinite quark mass, which is this blue points, you see a divergence, right? So then the next quark mass you have is 800 MeV. You have a pretty narrow peak. As you go to the 400 MeV, it slightly broadens, maybe, but the errors are too large. So the problem with this old data at larger quark mass is also not very accurate. And finally, when you go to the physical quark mass, or nearly physical, it's not quite exact, but it's close enough, you have a very broad peak, right? And yeah, so this deconfinement transition, which essentially shows how quickly the Polyakov rises and goes to a asymptotic value, that gets washed away as you decrease the quark mass. So the deconfinement feature of the transition become more and more washed out as you go from large quark mass to small quark mass.
Sorry, as the quark mass decreases, the deconfinement transition.
This deconfinement transition becomes less and less visible, right? So it becomes smoother and smoother, right? At the heavy quark mass, even it's a crossover, the deconfinement transition in the Polyakov group is still kind of very prominent. But as you decrease the quark mass, you see already in the Polyakov group, it becomes very smooth, right? So it's not just a shift, it's just that this rise of Polyakov becomes kind of very slow and very smooth as you decrease the quark mass.
Another thing is whether decreasing dB radius correspond to the decreasing SQ.
Yeah, so the peak, you may say that the peak, the height of the peak also decreases, right? So it's a width, this increases and the height decreases. So SQ comes down a lot. So here it was around 8, and here just 4. So it decreased by a factor of 2. And it's true, well, let's say it's true at low temperature, at the peak. If you go to the high temperature, it's opposite, because then actually it becomes bigger. So it decreases at TC and below TC, but it seems to increase at high temperature.
Maybe it is a silly question, but what I understood that for NF equal to 2, okay, so the mass of pion compared to NF equal to 2 plus 1, NF equal to 2, it should be less than 161 MeV. So what I understand is the quark mass, like the mass of pion we get after after adding the quark mass, and there is a effective constituent quark mass, then we get the mass of the hadron or mass of the meson.
I mean, now the quark mass in Lattice QCD is input parameter. It's a parameter of Lagrangian which you have to put in. So when you kind of start your code on computer, you have to put some quark mass in there, and you don't know what it is, right? So you have to first guess and then fine-tune it such that you get the hadron mass, ideally what it is in the real world. Of course, you could also ask the question, well, if we would have some different quark masses, then in the real world, what would happen then, right? So you could sort of say play God and kind of imagine different universes, multiverses, where the quark masses are not what they are in physical nature. Of course, when we want to do physics, real physics, well, not kind of theoretical understanding of QCD as a theory, we got to tune the pion mass to be what is in the nature, 138 MeV. So we tune our bare quark mass till we get the pion mass to be what is the particle data group says. Now, that's what you should do in principle. Of course, when we do the practice, because we don't know, well, where it should be, we just pick a gas, and if we run out of computer time, we have to stick to it. So you may say that the fact that it's 160 is just unfortunate fact that when we did the tuning of our parameters, we were not doing a very good job, and we kind of stuck at this value. But one of the reasons we didn't improve it in the first round, because that is so close to the physical mass of 140, 138 MeV, that this 20 MeV difference in most of the quantity we're calculating is small enough compared to the statistical errors that we don't care. Because if you do a very precise study, then you better tune it to the physical value. So we just stopped here because we say, well, it's kind of close enough that whatever, we know roughly how the quantity depends on the quark mass, and the difference between this value and the physical value, that wouldn't result in a big shift in most of the quantities we're interested in. So we just stopped here, but in principle, if we were purist and want to do a really good job, we would retune the quark mass and make it 138 MeV. But then, of course, you could ask the question, okay, if you imagine a world, a QCD, where the quark mass in your Ramanujan wouldn't be what it is, or in the real world, but something else, much larger, how the deconfinement transition would happen. And then, of course, you could go to 400, 800 MeV and study your entropy of a static quark as functions of quark mass, and see how you approach the limit where the quark mass becomes infinite. Of course, for historic reasons, that wasn't done for that reason. It was done simply because these are old calculations which were done at the time where we just couldn't afford running calculation at the physical quark masses. Are way too expensive, so we use large quark mass to reduce the cost of calculation. So early days calculation could have been done only at 800 MeV pi mass. So that's what we had then. Now, of course, we use this calculation, this old calculation, somehow to understand the quark mass dependence. So it's kind of, in some sense, both. It's the inability to go to the physical limit and the desire to little bit understand how the physics depend on the quark mass.
Questions or comments? So if not, I have a question. Okay. So my question is related to the spectral function that you showed. So as for example, the vector spectral function, we can relate it to the lepton pair production, right? So, yes. So
I mean, talk about it. I mean, there's an entire lecture series I could give about spectral function.
Yeah. So, so my question is, when you come below this threshold, you talked about it, but I didn't understand it quite. So how you physically look into that? I mean, when you come, so that part. So when you come below the threshold, how exactly you relate your spectral function?
So if you ask what would be the lepton rate coming out of a very hot plasma where you don't have row mesons or anything, then the statement is that about some threshold, it just will be given by this. Okay, so that means essentially Drell-Yan production, but now from the thermal source. So that's a physics interpretation of this part of the spectral function. If you go to lower temperature, of course, the spectral function wouldn't be quite like this. There will be a row peak, and that will also contribute to the lepton. But this spectral function essentially is directly proportional to the lepton rate.
Right.
So now the transport peak is interesting, right? Because it's kind of an on-shell photon, right? If you would, of course, photon corresponds to omega equal p. So this transport peak would mean that from a thermal plasma, in principle, you could emit a very soft photon, right? And this, so there is a relation between electroconductivity and photon emission rate. So on one hand, you could say, well, this part of the spectral function here is electroconductivity. Well, let's now think of m being small, because of all the light quark mass. Or the photon rate, because if you emit essentially a static photon, well, it's kind of weird to think about kind of non-moving photon, but let's say you do the same calculation that's exactly for zero momentum. Of course, you could do the same calculation at slightly non-zero momentum, it will be similar, more or less. So there is this limiting cases where you could say, well, the emission of very soft photons is related to electroconductivity, and everything is encoded in this part of the spectral function.
Okay. So any other questions, comments?
Did you have a question?
Yeah, for the heavy versus light quark, for the heavy quark, this transport peak is due to the diffusion. And for the light quark, maybe because of
it's also diffusion. Electric conductivity is I mean, if you wouldn't have diffusion of light quarks. Imagine a ideal Quark-Gluon Plasma. A quark just would fly, kind of flies through, right? So it means free fast would be infinity and the conductivity would be infinite, right? Because there is no dissipation. As that means that, of course, infinite electron conductivity means that you have a delta function omega equals 0. So delta function omega equals 0 is just infinity, right? So now if, of course, even the light quarks scatter in the medium, or the light, I should say, also the light quarks scatter in the medium, and that makes the electric conductivity to be finite. So the spectral function omega equals 0 is not infinite but finite. So, and that's the diffusion of a light current or light quark. So it's just rescattering, of course. So in principle, yeah, so you could think of, as long as you have a conserved charge, there's always a diffusion constant associated with a conserved charge. So it's not only, of course, it's not you cannot think of it as a Ramanujan process, right? But in effect, in the very soft limits, so around omega equals 0, is basically the same. It's just there is no Ramanujan dynamics you could associate with that.
And how are the relative widths of these?
Well, the relative width is 1 over T over M, right? So, of course, if you have M equal to 0, then that's not well defined. So you could only say that, well, let's M to be equal to T, because at the end of the day, M, the effective quark mass is always, you have some quasi-particle mass, right? Let's of order T, then somehow you say, well, it's this formula applicable as long as M over T, and then of course you have the width will be just G squared to T, G to the force T is a light quark. So it's just, you can't extrapolate it, but so you somehow, to go to the light quark limit, you have to substitute M of order T, and then you get the right order of magnitude, right? But you could work it out exactly, setting M to 0, and then you get that the width of the transport is just G to the 4T. Whereas the heavy quark limit is the same, but now with additional factor T over M. So heavy quark limit, you have a very narrow transport peak, and in the light quark limit, the width of the transport peak is just given by as a inverse coupling constant, at least in the weak coupling. And then you can separate the strong coupling, and that means that if G is large, then this could be arbitrarily wide.
Yeah, so I have two kind of questions, which are probably dumb, but I'll ask them anyway. So here you're talking about conserved currents, right? So say you take a current which is not really conserved, but perhaps conserved on a relatively long time scale. So I'm thinking particularly about axial charge currents in high temperature phase, right? What would do you have any idea what the spectral function of such an object would look like?
Very similar. For example, you could, and that's an interesting question. For example, you go to Sharmonium case where you have a heavy quark, right? Not too heavy, but reasonably heavy. And you look at other, in particular, you look at the axial charge, which is not conserved. You look at the scalar density, which is not conserved. You calculate the spectral functions, or at least estimate the spectral function based on the correlation function you have. They all show some sort of peak here. And it's clear why, because if you have a approximate non-relativistic system, it's not only the net charge which is conserved, the particle number is conserved. So each of these correlator have kind of an approximately conserved particle number, even the scalar one, and you get the transport peak. So for example, if you calculate the scalar correlator in the light quark sector, there is nothing in there. There is no transport peak. But if you make the heavy quark mass to be large enough, some small transport peak appears. If you go to the chiral limit or close to the chiral limit, you consider in the vector current and axial vector current for very small quark mass at high temperatures, they're almost identical. With vector current, you have this transport peak, and because the axial vector correlation function is almost degenerate with the vector, you would say, well, it only could happen if also the axial vector has a similar transport peak. And the difference is some sort of details which kind of subleading in either 1 over m or m, depending whether in the heavy quark or light quark limit.
So you're saying, so I mean, so the particular one,
So
the particular one I would be very interested in would be the light flavor axial current, right?
And my statement
Because there should be Sphaleron effects, things like
right.
this.
So
in
my
there,
statement is that as a light flavor axial current is basically you have the same transport peak as in the vector.
So essentially you see no signs of axial charge non-conservation there, if you want to. Okay.
Of course, it's kind of encoded in the width, right? So what I'm saying is that it's a non-conservation effect is a difference in the width of the vector current spectral functions axial vector, but on the lattice you probably don't see the difference.
So if I may, so one more question related to that. So does the fact, so if rho of omega over omega has an intercept, a non-zero intercept at zero, does that automatically mean I have a conserved charge somehow, or can that happen somehow under arbitrary
I think it somehow has to mean the conserved charge, but so what we don't know, of course, I certainly don't, if you have an approximately conserved charge, is it exactly proportional to omega? What I know for sure is that if you have an approximately conserved charge, you have some structure like this, but what it does right here, that I don't know, because I have no way to calculate it on the lattice. But this genetic feature that you have some like a transport-like peak, let's say, is definitely correct. But how it exactly behaves of omega zero, that I don't know.
Yeah. Okay. Thanks.
I have one question.
It's on.
Okay. So in your entropy plot, that there is a peak, right, at the transition temperature.
I'll have to go backwards.
Then the entropy figure, that where you showed that entropy is a function of temperature. So do we expect that the peak will become sharper as you increase the number of colors?
I think so, because if you fix the number of flavors to 3, 4, whatever number, you go to NC to infinity, of course the transition will becomes closer to a phase transition. In fact, for any fixed NF and NC to infinity, you must have a first order phase transition, simply because in the deconfined phase you have a huge number of degrees of freedom, while in the confined phase you have hadrons. So for any fixed NF and infinite NC, you approach, or you have a first order phase transition. So I guess a larger NC means that you're getting closer to this regime where you have a first order deconfining transition. So yeah, if you fix NF to 3 and you go to SU4, this peak in the entropy should be higher, right? Or if NC is large enough, it of course will diverge because you will have a first order phase transition. Deconfinement first order phase transition, even in full QCD.
Okay. So for NC is equal to 2, it's a second order transition, right?
For NC equal to 2 is a second order transition for pure glue. So if you add any fermions, you immediately becomes a crossover. So if you have SU4, for example, then I don't know, probably still a crossover, but any larger gauge groups, you have a chance of generating a first order phase transition even for non-zero NF.
So okay, another question is that about that EE correlator you are talking about using reducing error by multi-level algorithm. So the E field, I think that it includes connect 2 time slices, right?
Right.
So how do you ensure that multi-level algorithm can be worked there, because multi-level is based on the locality of time slice, right?
Right. So in full QCD, the multi-level doesn't work. Right. So once you have a non-local action, and then of course if you have a fermion determinant in the game, the action becomes non-local, so you don't have this multi-level algorithm. For that reason, nobody so far even attempted to do this calculation in full QCD.
Okay.
So this strategy of calculating the heavy quark diffusion has been worked out in pure glue, so we know the answer. And I don't see at the moment it's to be done in full QCD for exactly the same reason that multi-level doesn't work. Now people have other ideas like simulating fermions using multi-boson algorithms, and then maybe you could have some sort of local algorithms as well, so some sort of multi-level, but that's work in progress. Nobody knows at the moment how to do it.
And what is the link integration? That is multi-hit?
That's essentially multi-hit, right?
Thanks.
Or comments? Okay, if not, let's thank the speaker. And before we disperse for the lunch, since this was the last lecture by Peter, so we should really thank him once again for the set of lectures that he has given.